Hi everybody, in this video I'm going to be talking about function transformations using vertical shifts of graphs of functions. To understand what this means, let's take a look at our first example here, which says given y equal to f of x, draw y equal to f of x plus 2. So, we have this graph here of a function y equal to f of x, and using this we have to draw the graph of y equal to f of x plus 2. In other words, we have to transform the graph of f of x to f of x plus 2, hence the name function transformations. So, the best way or a very helpful way to think about such situations where function transformations are involved is to interpret functions as machines. So, think of this original function that you have here f of x as a machine f into which you put in some input and you get some output. So, let us say that for some input x naught, the output that this machine produces is y naught, and therefore x naught comma y naught will be some point on the graph of this function. Let us say it is this point over here and this is x naught comma y naught. Now, what I want you to think about is what happens for this point or to this input output pair if the machine f is replaced by the machine f of x plus 2. So, now let us imagine a new machine which is f of x plus 2, which I am writing as f plus 2, and let us think about what will happen if we put in the same input into this machine. So, if I put in the same input x naught into this machine, what output will this machine produce? Well, because the original machine is producing y naught as the output, the new machine should produce y naught plus 2 as the output. So, the original input output pair x naught comma y naught for the original function should correspond to x naught comma y naught plus 2 for this new function f of x plus 2. So, very simply put, what should happen is that this point here x naught comma y naught on the original graph should actually move 2 units up because the y coordinate is increasing by 2. So, this point should move 2 units up, and corresponding to this point, the new point on this graph of f of x plus 2 should be 2 units higher. So, let us just do that and move this 2 units up over here, and this point here is x naught comma y naught plus 2. And the exact same thing is going to happen for every other point on the graph. So, for every other point on the graph, the y coordinate will increase by 2, and therefore, what should really happen is that the entire graph should lift up by 2 units, and that is really the transformation that will happen here. So, let us just look at what it will look like, and here I have drawn it for you. So, this was our original graph y equal to f of x, and this is the new graph y equal to f of x plus 2, the dotted graph, which I have plotted using a graphing tool. So, it is very accurate, and you can observe here that every point on the original graph has lifted up or translated up or vertically shifted upward by 2 units. For example, if we take this point over here, this point has gone up by 2 units over here, and let us take this point over here, this point has gone up by 2 units, and we have this new point over here, and you will have the exact same behavior everywhere. So, let me take this point here, and this one has gone over here to this point, new point on the new graph. So, the entire graph has lifted up by 2 units, and that is really the transformation that has happened here. So, this is what is called a vertical shift of the graph. Because you have added 2 to the function, you have essentially vertically shifted the graph of f x upward by 2 units. Now, what if instead of adding something we subtract something? So, given y equal to f of x, draw the graph of y equal to f of x minus 3. So, the argument is exactly the same. If the original function f produces, let us say for some input x naught, it produces the output y naught, then this new function f minus 3 or f of x minus 3 will, for the same input x naught, produce the output y naught minus 3. So, the original input output pair x naught y naught will correspond to the new input output pair x naught comma y naught minus 3, which means that if you take any point on the graph, so let us take this point over here, let us call it x naught y naught, this point will essentially shift downward by 3 units to give us the corresponding point on this new graph. So, if I shift this 3 units downward, the new point or the point corresponding to this point on the new graph should be this point here. And this exact thing or this exact vertically downward translation is going to happen for every point on the graph, and therefore the entire graph will shift vertically downward by 3 units. And here's what that would look like. I've actually once again plotted it using a graphing tool. So you can observe that every point has shifted downward by 3 units. If you take this point here, for example, this point has shifted down by 3 units. Let's take this point over here, once again the same behavior, and you can observe this happening for every point on the graph. So the entire graph has shifted vertically downward by 3 units. So this is a vertical downward shift because we are subtracting something from fx. Okay, so that's essentially the whole idea of vertical shifting of graphs. If you have to transform y equal to fx to y equal to f of x plus something or minus something, and here I am thinking of c as some positive constant. So either you are adding a positive constant to c to f of x, or you are subtracting something. So if you are adding something to the original function, so your original function in this figure here is this white curve that you see in the middle, and if you add some positive constant to this function to get f of x plus c, then you essentially shift the graph vertically upward by c units. And if you subtract something instead, f of x minus c, then you essentially take the original graph and vertically shift it downward by c units. So to make the visualization clearer for you, let me actually also show you this behavior in a simulation. So here's a simulation of a function. Here's a function graph, and think of it as the function y equal to f of x, and what I can do here is plot y equal to f of x plus c and y equal to f of x minus c, and I can vary the value of c. So let me first plot y equal to f of x plus c, and right now c is equal to 0. So the new graph is equal or equivalent to the original graph, but let me now increase the value of c. So if I do that, if I increase the value of c, you can observe that the new graph is a vertically upward shifted graph version of the original graph. So right now I have set c equal to 3.9. So the new graph is the original graph shifted upward by 3.9 units. So that's vertically upward shifting, and then if I plot y equal to f of x minus c, my graph should translate or shift downward. So if I increase c now, you can see that the new graph is a vertically downward shifted version of the original graph. Here I have set c equal to, let me set it to 3.3. So my new graph is 3.3 units, is the original graph shifted downward by 3.3 units. So I hope that this simulation has made the behavior of vertical shifting very clear to you. Now let's do a couple of questions based on this concept. So question number 1 here says, the graph of a function y equal to f of x is shown below. What is the minimum value of f of x plus 3? So f of x plus 3 will simply be curve or a graph that is just like this, but vertically shifted vertically upward by 3 units. So to plot f of x plus 3, you would just take this graph and shift it vertically upward by 3 units, which means that the new minimum for f of x plus 3 will be the original minimum shifted upward by 3 units. So the original minimum in this graph is clearly this point over here, and this seems to have a y coordinate of minus 4, and therefore the new graph of f of x plus 3 would have this minimum go up by 3 units. So the new minimum would lie over here, and then your graph would be something like this, but I am not going to plot the full thing. I just need to look at my minimum point, and that new minimum point will have a y coordinate of minus 1. So f of x plus 3 will have a minimum value of minus 1 because f of x had a minimum value of minus 4. So that's the answer to question 1. And now let's look at question 2, which says the graph of a function y equal to f of x is shown below. does y equal to f of x plus 8 have any real zeros? So, y equal to f of x plus 8 would be this same graph shifted vertically upward by 8 units. Now, if you observe this graph and see the minimum point over here, this minimum point has a y coordinate that lies above minus 8. So, the minimum point has a y coordinate that is somewhere between minus 6 and minus 8. So, if you shift this graph vertically upward by 8 units, the minimum point here will go above the x axis, and therefore, the curve of f of x plus 8 will never intersect the x axis at all, and therefore, y equal to f x plus 8 will not have any real zeros. So, pretty straightforward, right? So, that is what vertical shifting is all about. I hope you understood it and I hope you liked it. Let me know what you think in the comments.